Okay, so we are now going to cover the root test for testing conversions of infinite series. And it's natural to think of this as a close relative of the ratio test. They're very similar. So here we have the root test. And so again, we're dealing with a series that has positive terms. Let's just say strictly greater than 0. And this time we take the nth root of a sub n, and the limit of that as n goes to infinity, defined as our rho. We have the same convergence criteria for that rho as we had in the ratio test. If this limit as n goes to infinity of the nth root of the nth term is less than 1, we have a convergent series. If that limit of rho is greater than 1, we have a divergent series, and it's inconclusive if rho is equal to 1. And the intuition is very similar to that of the ratio test. So what this limit tells us is that for large n, the nth root of a sub n is approximately equal to rho. Well, raise both sides to the n power and you get a sub n is approximately rho to the n, which means this looks a lot like the nth term of a geometric series with a ratio term of rho. And remember, rho is always greater than or equal to 0 because the terms are greater than or equal to 0. So this nth root is greater than or equal to 0. So you have this convergence criteria similar to the geometric series. If that rho is less than 1, the terms in this look like terms from a convergent geometric series when n is big. If this rho is bigger than 1, then these terms, when n is large, look like terms from a divergent geometric series. And if rho is equal to 1, the test is inconclusive. So we're going to see how you can use this in just a moment, but we also have two results that come up a lot with the integral test. And these are things that you would have learned earlier in calculus. So one result that you can quote these: the limit as n goes to infinity of n raised to the 1 over n equals 1. The way that you would derive this is actually L'Hopital's rule. You would take logs. You have an infinity to the 0 indeterminate form here. You would take logs, transform it to an infinity over infinity indeterminate form, use L'Hopital's rule, and get this answer. And then the other, which you learn in differential calculus, is that the limit as n goes to infinity of 1 plus x over n raised to the n is e to the x. You also can show this using L'Hopital's rule. This is usually also something that comes up a lot when you're learning about compound interest type of math. Both of these you can cite as theorems. And again, they tend to come up when you're using the root test. So let's see some examples with the root test. So our first root test example, here we have this sum n to the n over 2 to the n squared. Now, maybe hard to make what we have here. Hard to get a sense of what this is doing. But let me point out something. When we have done our races, we have said that we had factorials. So remember, we were looking at how fast these different classes of functions race to infinity. We had logs, were the slowest, polynomials, beat up logs, exponentials, beat up polynomials, factorials really outrun exponentials, and then n to the n outruns factorials. And in each of these races, any pairing that you do here in a round robin racing tournament, the result will always be that one is dramatically faster than the other. So think Bugs Bunny versus the tortoise. So this n to the n goes to infinity very, very quickly. But of course, 2 to the n squared will as well. It may be a little bit hard to get a sense of who wins there. So this is a tougher one to see what will happen intuitively. But let's use the ratio test, the root test. And one of the reasons why we're going to use the root test is we see that we have exponents that involve n in both top and bottom. And the root test is handy because taking the nth root will undo that nth power. So the root test may work well for this example. So rho is the limit as n goes to infinity of the nth root. So we have this n to the n over 2 to the n squared raised to the 1 over n. And remember your rules for exponents. The exponents will multiply. So we'll have n to the n, and that exponent of n is times 1 over n. And in the denominator, we have 2 to the n squared, but that n squared is multiplied by 1 over n. So this becomes the limit as n goes to infinity of n over 2 to the n. We already know from what we've studied before, this will end up being 0 because this is your exponential in the bottom versus polynomial on the top, and infinity over infinity indeterminate form. But we know polynomial goes to infinity much more quickly than n. So we know we're going to get 0. But again, we show that using L'Hopital's rule. This is the limit as n goes to infinity of 1 over, and remember the derivative of 2 to the n is 2 to the n times natural log of 2. And that we see is 0. Well, that was rho. That was this nth root of our summand. And what we care about is that this is less than 1, which means the series converges by the root test. So in fact, 2 to the n squared is going to infinity much faster than n to the n. So these terms are racing to 0 at a fast enough rate, actually very fast. So this series converges by the root test. Again, when you see powers of n in the top and the bottom, especially if n is in the base and the exponent, the root test is often a very useful test. Let's do another example. Here we have n factorial to the n, and then over n to the n squared. Another very natural candidate for the root test because we're seeing an n term in both the exponent and in the base. So again, form rho is the limit as n goes to infinity of the nth root of that summand. So that original summand all raised to the 1 over n power. And then, of course, our rules for exponents. The exponent multiplies. So 1 over n multiplies by n here. And then 1 over n multiplies by n squared down in the bottom. So we have a result of n factorial over n to the n. Now, this is actually the race that I alluded to earlier. So remember, we said this n to the n is new on the block, and so we want to see how it fares in a round-robin tournament against these. But right now, it's paired against factorials. We're going to see that it totally blows factorials away, which means that it will do the same to these slower increasing functions, exponentials, polynomials, and logs. So we're going to actually confirm that n to the n in this, with all these different racers, n to the n is going to be the fastest growing of all of them, and dramatically so, using this race here. And the way we do this is, let's actually write things out. This is the limit as n goes to infinity. In the top, you have n factorial is n times n minus 1 times n minus 2 down to 3 times 2 times 1. And n to the n is n copies of n. And what we're doing now, what we do now, is we pair these up top and bottom. N over n, n minus 1 over n, n minus 2 over n, down to 2 over n times 1 over n. So we rewrite this as the limit as n goes to infinity of exactly like that. So we have n over n is, of course, just 1. N minus 1 over n, n minus 2 over n, 3 over n, 2 over n, 1 over n. Now, what we're going to do is actually stop doing equalities. Remember what we care about with rho. What we care about is whether or not rho is less than 1. If rho is less than 1, we get a convergent series. If rho is bigger than 1, we get a divergent series. If rho is equal to 1, we don't know. We have to go use something else. But we're going to actually set up here to show that rho is less than 1. So we're not actually going to explicitly compute rho. We're just going to find an upper bound for it and show that that upper bound is smaller than 1, so rho is smaller than 1. And the way we do this is we note that, again, that n over n is just 1. Then we have n minus 1 over n. But n minus 1 is bigger than n minus 2. So we can replace this n minus 2 with n minus 1. And we can do that for each numerator thereafter. That's making everything bigger, hence the less than or equal to. So we can think of it as we are enlarging this expression by replacing all those numerators with n minus 1. But we then note that this, how many of these are there? Well, remember we started out with n of these terms, but the first one turned out to just be 1. So there's a total of n minus 1 of these terms. So we can rewrite this entire expression as the limit as n goes to infinity, n minus 1 over n. Well, there were n minus 1 of them. So it's n minus 1 over n to the n minus 1 power. We then rewrite this n minus 1 over n as, well, we have limit n goes to infinity, we have n over n is 1, minus 1 over n to the n minus 1. And now, looking at this expression, recall, we mentioned this at the beginning of the class, that the limit as n goes to infinity of 1 minus x over n to the n is e to the x. This is almost the case for x equals minus 1. It might be easier to think of this as 1 plus negative 1 over n. We just need the denominator n here and the exponent here to match. We don't quite have that. So what we can do is rewrite this as the limit as n goes to infinity, using our rules for exponents, 1 plus negative 1 over n to the n times 1 plus minus 1 over n to the minus 1. This first term, we can now directly cite our theorem. This is the case where x equals minus 1. So this term here will be converging to 1 over e, or e to the minus 1. This term here, the minus 1 over n goes to 0, and so this whole term goes to 1 to the minus 1, which is 1. So this is e to the minus 1 times 1, or 1 over e. E is between 2 and 3, which means 1 over e is less than 1. So our conclusion is our series converges by the root test. So this would qualify as a tough question. What we showed here, we actually didn't compute rho. Rho is not 1 over e. But we showed through a inequality that rho is less than 1 over e, which is less than 1, which means whatever rho is, it's less than 1, and therefore this series converges by the root test. So this example gives us there's kind of two reasons to do it. One is because it's a good, challenging root test question. But two, it also gives us a chance to look at this race. So because this series converges, so these terms are going to 0 quickly enough for this sum to be finite, that's also a confirmation in here. Because this limit is less than 1, it means that n to the n is racing to 0 faster than n factorial. So this does confirm our n to the n being the fastest on the block when we're racing these different functions against each other as n goes to infinity. So again, root test, when you see something that has an n in the exponent top and bottom, as well as something with n in one of the bases, the root test is often a natural choice.